Hi, good morning, and welcome to the ZP Developer Zone vlog and podcast. So we do this every week for members of our ZP Developer Zone, and we answer sort of technical questions regarding, around electrochemistry and also sort of commercial applications as well. So let me jump into it and say today is the 19th of January 2023, and these are the questions that have come in for this week. Now, don't forget that we have our ZP Academy. That's a free, there's at least two free courses on there. It's a resource for people who want to learn about biosensing and electrochemistry. We have our webinars. So this is an example, that we give out technical outputs every week at 8 a.m. London time. We have collaborations. These are strictly with, I would say, academia. When we say collaborations, we also list jobs. We also have our ZP Developer Zone, and we also have our workshops. And workshops is something that we've really ramped up in 2022, and we continue in 2023. So if people have technical questions or technical things they want to discuss, from wearables, glucose and lactate, to IVD, in vitro diagnostics, to immunoassays, to molecular assays, then our workshops are a really excellent resource for that. I've put a link underneath the workshops now, let's say, and any kind of links that you see popping up there, I've also pasted them or posted them underneath the video. This is just because we've just actually gone beyond 2,000 subscribers, which is really nice. So if you can you like these videos? And also, if you're not subscribed, please subscribe. We do put out content quite a lot. We do try to lead with a lot of, there's a lot of educational material, etc. So we do try to put out quite a lot of material through the, for example, the YouTube channel. Anyway, questions this week. We've got question 1, which is about depositing enzymes, and I will discuss that. Question number 2 was about wearable biosensors, and whether they were label free, and I will discuss that. I should say question number 2 was about molecular assays, question number 3 was about wearables, and question number 4 was about blood gas analyzers, and I will jump into that. And question number 5 was about gold electroplating and functionalization, and I will answer that as well. So when it comes to depositing enzymes, I would say this is something that we do teach at the workshop, and it's in fact on this geometry that everyone who comes to one of our workshops makes at least one biosensor, and they make it by hand. We've had, basically excellent yield. Everyone who attempts to make one succeeds in making one. Now, the reason I bring this slide up is because I think we make really excellent screen printed electrodes, for example, and upon those screen printed electrodes, people are forming biosensors. So it's probably worth me saying that what we're looking at here is a signal from a biosensor built upon a screen printed electrode, actually built upon this hypervalue screen printed electrode. This is 3 sensors. So you can see they're very close in terms of their performance. This is another 3, this is another 3, this is another 3, this is another 3, and this is another 3. So 3, 6, 9, 12, 15, 18. That's 18 sensors, all showing, I would suggest, excellent performance. And they're all made on the screen printed electrode, and they've all undergone 2 functional tests. So what I'm going to do now is describe the functional test. So we take this hypervalue electrode, and we functionalize it. This is through an electrode deposition process, and so I will be showing this video later on again. When it comes to the electroplating questions later on, I'll be showing this video, but this is a robot that we have at ZP. But I'm just describing that we do electrode depositions on these electrodes. And then the next part we do as well. Now, I'm showing here robots. So we do have these robots that can do very precise deposition. But if people are trying to make biosensors on screen printed electrodes, and so the data I just showed just a second ago, where it was kind of about 18 sensors. They were made by taking a pipette and just putting down microliter droplets in a row and just spreading them with the tip of the pipette. So we do have this question coming in a lot. Well, how do I functionalize these? People like these circular electrodes. You know, they come in, they can do a pipette, it spreads out. But of course, we're always designing, and I've said this before, with our mind on actually making a product. You know, so there's a good reason why our electrodes is shape. They work particularly well in microfluidics later on. So we've obviously got an eye on what's called, you know, in vitro diagnostics. We're not just trying to make sensors that kind of work well in the R&D phase. We're generally trying to make sensors that eventually become products. When I say sensors, I should say electrodes as well. So just to kind of quickly summarize this, and I'll just flick back a little bit. These 18, I think they are, no, yeah, 18 sensors, so they're all in triplicate, were all made on these screen-printed electrodes. So you can see that the repeatability of our underlying screen-printed electrodes are really excellent. And they were actually made, you know, by hand, though I bring the robots up to illustrate that we can actually do this by robotics as well. But we made them by hand in this particular case, and we did it by electrodeposition and then functionalization using a pipette. So the answer is, if you've got a fine handle and the right size pipette, you should be able to functionally test these sensors. I just want to sort of discuss now the connection between photospectroscopy and electrochemistry. So bear with me, I'll go pretty quick on this subject, but we do have people who have who watch this channel or interact with Zimmer Peacock who have a background in kind of photospectroscopy, and then, you know, there's people like Zimmer Peacock, and we're quite interested in voltammetry. This is just one of our products, and I do have a link for it. And in this product, we've actually put a well. And so I just want to kind of make this connection that if you can do an assay by essentially photospectroscopy or absorption spectroscopy, you can also do that assay by electrochemistry as well. So a molecule that has a sort of a good absorption spectrum, especially in the kind of longer wavelengths below, or rather wavelengths greater than the UV part of the spectrum. So this is those electrochemical, not electrochemical, this is the absorption spectrum for ferricyanide, and this is the voltammogram for ferricyanide. The spectrum of ferricyanide and the fact that it's colored is a great indicator that ferricyanide is electrochemically active, and it is electrochemically active. It's a sort of, you know, classic, let's say. The electron, there's an electron transition that gives you the color and therefore the absorption spectrum of ferricyanide, where electrons are transitioning between the orbitals in ferricyanide. Now, electrochemistry is actually quite equivalent to that, because in electrochemistry we have electrons in the orbitals of ferricyanide, and they transition essentially to the orbitals in the metal. And it's that transition that gives us the oxidations and reductions. So I want to say this, that if you can make an assay work by photospectroscopy, it's 99% sure that you can actually do it by electrochemistry as well. The electrochemistry is actually, in part, electrochemistry comes from the dye industry, that a lot of dye molecules are intrinsically electrochemically active. So dye molecules are colored molecules are electrochemically active. So I just want to say that if you are working in the spectroscopy, let's say space, and I mean photospectroscopy, you can just transition, you should be able to just transition those assays across to electrochemistry. And one way of doing it is actually, rather than just doing the experiment in the cuvette, is to do the experiment in one of our sort of electrodes with this well on it. But if you want the enzyme on that surface, then yeah, you have to come in with a pipette and just do 3 drops, spread it with the tip of the pipette, and you should be good to go. And if you are struggling, please come to one of our in-person workshops. I know that some of them are in the UK and in Norway, so it's not always easy, but there we can at least sort of try and show you how we're doing it. At ZP, we do have a very strong molecular biology group, really experienced practical people. And so when people come to us for molecular assays, they're kind of concerned about amplicon contamination. And so at ZP, when we're doing molecular work, we actually have a very unidirectional workflow where we have a prepping area, we have a template area, we have a testing area, and then we actually have a amplicon lab. And these are physically separated regions in the building, or areas in the building, and you can only go forward in the workflow. You can't then cycle back and sort of essentially try and bring or accidentally bring contamination from downfield back into one of the labs that's upfield of it. So at ZP, we do a lot of molecular assays, and if you're interested in doing molecular assays, obviously avoiding contamination is one of the important things to consider. And at ZP, we're very strict on this, and we have we take a lot of PPE to essentially the personal protection equipment is not to protect us; it's actually to protect the assays from us. But we do a lot of this work in class 5 zones. So these bubble hoods, for example, you can see the extractor on the back there. They are class 5 zones sitting in a class 7 clean room, and then we take a big effort to keep PPE on so that we don't end up contaminating the assays. So that's something that we're quite strict on at ZP. We do have a lot of experience in making sensors for molecular assays. We've got different sort of configurations where we can bring the sensors or bring the electrodes into the things like into the PCR tubes or the Eppendorf tubes, or we have sensors where we have these little wells on top so that we can do the molecular assay in those little wells. But we do have a lot of experience in that molecular biology space, let's say. In particular, in the last few years, there's been a lot of LAMP assays come our way. And in that, we've not only done the molecular assays, we've also done the equipment development as well. And so we end up designing instruments with things like Peltier plates in place so that we can bring the assay to temperature, hold it at temperature, and then bring the assay back to temperature as well. So I think Peltier has more of a power need than what we could call ohmic heaters, but Peltier is great because it can heat and cool. So we're quite used to the temperature requirements, for example, in molecular assays. Some people in this space are also quite interested in a molecule, or sorry, I should say, an enzyme called Luciferase, and this is also something that can be used with electrochemical techniques and electrodes as well. So, question number one, I've hopefully was about really how to functionalize those electrodes. I just said just do 3 little drops, and then I wanted to expand to the question and say that if you can do assays optically, you can definitely just transition to electrochemical. Question number 2 was about molecular assays, that we have a unidirectional workflow established. We're actually quite experienced on things like LAMP assays. And obviously, we're also experienced in building instruments for doing the temperature control on those kind of assays. We got this question that came through the YouTube channel. Somebody was watching really quite an old video of ours where we talked about wearable sensors. It's probably worth saying that we do a lot of workshops on wearable biosensors. So when people say to us label-free, what often means is that you're doing a immunoassay or molecular assay where you have a binding on a surface, and that binding causes a change in the surface, which we can pick up using techniques like impedance spectroscopy. So the quick answer is yes. If I was trying to make a wearable biosensor and my target was a protein, for example, then we would do a label-free sensor for that. And the modality here is electrochemistry. So I hope that helps to in part answer your question. Every time you see me put a little link down, I've already put it underneath the video this morning, so hopefully that will help guide people in. And don't forget, we do these workshops where we do actually do, or we discuss label-free quite a bit. And also wearable, I should say. I want to just transition now to blood gas analyzers. I have a link to this as well, but a couple of weeks ago, I think it's about the 5th of January, we covered a question that came in about blood electrolytes and blood gas electrolytes, and sodium, potassium, chloride, and pH came up in those days. And I discussed that then, and there's a link to the video. Since then, the questioner is also now interested in oxygen or PO2 and PCO2, partial pressure of oxygen and partial pressure of carbon dioxide. So I just want to say that we do have an oxygen sensor. Now, their specific questions were, they were asking here specifically, are our ISEs and PCO2s and PO2s used in commercial analyzers? The quick answer is that on the ISEs they are. I can't discuss it, I'm so sorry, but I can discuss other technologies that we have in the public domain that we've done for clients that are CE marked and approved for use with patients, and they're all using, in the end, everything that we sort of do with clients ends up being electrochemistry, and so we do have technologies that are on the market and are, they've been through their CE marking or they've been through their clinical trials. So I've put a link to some of that material there. Can the sensors be reused? And so, for example, I was talking to a client yesterday who's been continuously using our pH sensor for 9.5 days, and it's really quite stable. So the quick answer is you can reuse our sensors. Now, in this particular application, I have discussed this in the previous video. With these analyzers, there's a wash solution and there's calibration solutions, and that means it really helps with the reuse of sensors because periodically you can do a recalibration. So in the context of chemical analyzers, you can reuse these sensors because there's the ability to wash them and there's the ability to recalibrate them. The question here is, how do you assure somebody that you can supply them product? Now, obviously, Zimmer Peacock, we started in 2014, so we're in our 9th year. So the longer a company goes on, then the more secure you are, essentially. But we're just shy now, 1 year shy of being 10 years old, but we're 9 years old, so we've been around for a little while now. Just as a side remark, most companies go out of business within the first 2 years. I think about 90% of them have gone out of business in the first 5 years, and then when you get beyond that horizon, then you're a company that's kind of deemed to be stable. They're asking here about flow-through sensing because these chemical analyzers, the samples and the calibration solution and the wash solutions actually flow across the electrochemical cells. So at ZP, we do have some technologies where we demonstrate that we can take our electrodes, we can put them into a little flow cell, and we're flowing essentially solutions over the top. And I have some designs here for the idea that a sensor is in a flow cell. You have things like the sample itself, which could be blood sample in this case, switching valves, calibration solutions, and pumps. So at ZP, we're quite familiar with putting these electrodes into flow systems. I've said it before, but most of the sensors that we build, we try to build them for continuous measurement. And because we build them for continuous measurement, that also gives the ability to be reused. But that reuse works really well in this chemical analyzer space because actually you have the ability to do calibrations as well. So if there's any sort of damage or drift in the sensor, it can be calibrated essentially back out of the signal. And okay, if you see a link, then I've already put the link underneath the video, and I really hope that will help. In terms of PO2, we do have a PO2 sensor, and in terms of PCO2, we would have to develop a PCO2 sensor. We can do most sensors in what we call a proof of principle study, and maybe I should link to that there. That ZP, any links again are underneath the video, but we do micro projects, mini projects, and proof of concept / proof of principle. Of course, what we really do is we do full development, and essentially make entire systems that people can put into clinical trials, and then from clinical trials actually onto the market. But light engagements with us are micro projects, mini projects, and proof of concept. Just lastly, on gold electroplating, this came in just last night. Fortunately, I was actually traveling, and so I was able to essentially do it. The question here really is about, the question is around doing very bespoke or specific electroplating of material. So it's probably worth saying that we do have some very unique capabilities at ZP. So this is a whole series of electrodes. There's a working electrode on there, there's a reference electron, there's a counter electrode on there. And what's happening is we're going from bath to bath, but each one of those electrodes is electrically connected to, and so we're actually able to do any form of electrochemical technique that's been developed in the lab, be it sort of cyclic voltammetry, be it amperometry, be it potentiometry, etc. Any kind of electrochemical deposition, we can apply it to the electrodes actually through this robotic system. So that really helps us do very bespoke depositions that normally can't be done outside of a laboratory setting. And then, but once you've obviously got that metal down, the next phase is you need to actually functionalize it. When people are doing gold electrodes, they're often using some sort of thiol bond to immobilize antibodies or aptamers or receptors or RNA and DNA, single-stranded RNA, DNAs, etc., onto the surface. And so at ZP, we've got really excellent robots that really give us kind of precision, and we can come in there and do all sorts of scales of manufacturing using the robotic systems. And it's probably worth saying that we're very familiar with things like gold electrodes. These are all on our website, and these are from our sister company, Biosensors. They do a really excellent gold electrodes, for example, on PCBs. And these are all the links that can sort of give you an idea of the kind of gold electrodes we make, even though I realized in this inquiry you want to do a very bespoke gold deposition. But the fact that we do have robots that are essentially able to do any kind of technique that would have otherwise been developed in an R&D setting, we can program the robot to use those kind of waveforms and do that kind of deposition. It's probably worth saying that the kind of when we make gold electrodes and when we deposit and turn them into assays, we do a really good job on it as well. This is some work that we did in the past on making gold electrodes into biosensors. So depositing enzymes, we're just doing the deposition by hand. If people are struggling to do it, do come to a workshop. We'll give you some hands-on guidance. We are extremely experienced in molecular assays. Obviously, all through the pandemic, you could imagine how many molecular assays we were doing because of all the pathogen testing that was going on. But we did do an awful lot. And we do have unidirectional workflows in order to avoid amplicon contamination. We can deal with Luciferase if that's of interest. And we can also build systems for doing temperature control, for example, in lamp assays or PCR using... in the case of PCR, it'd probably be a Peltier because you want to heat and then cool as well. Wearable biosensors come to one of our workshops, but we would use impedance spectroscopy, for example, if we try to make a label-free sensor. Blood gas analyzers, we've got all the sensors that were on that list, apart from PCO2, which we could do through a proof of principle study. We are ISO 13485, and we do have experience in doing sensors in flow, and we do have customers on the market with technologies that we've developed for them and gotten them through clinical trials. And of course, electroplating, especially with processes that have come out of universities, that might be a bit special. It's not necessarily constant current or constant potential, but there might be some more unusual waveforms, we'd be pretty good at that, as similarly massive sensors, and we're very good at functionalization as well, which is, coming in with a robot and putting very specific droplets in very specific places. So I want to say thank you. Really, if you have any questions of ZP, don't hesitate to reach out to us. As you can see, even if the questions come in late on a Wednesday, we try to shoehorn them in at the last minute on a Thursday in this webinar. All right. Otherwise, take care. If you've got any questions, reach out to us at ZP, and I will finish up and start the working day. All right. Take care. Bye-bye. Take care.